Titan II, the largest and the most powerful ballistic missile in our arsenal. 54 are currently deployed at 3 Strategic Air Command locations: Davis-Monthan Air Force Base, Arizona; McConnell Air Force Base, Kansas; and Little Rock Air Force Base, Arkansas. These underground launch sites are hardened against nuclear attack. 1978 marks the 15th anniversary of Titan II's operational readiness. Standing 103 feet tall with a 10-foot diameter and weighing 150 tons, Titan II can be up and out of the silo in less than a minute after receipt of launch command, hurling its payload at speeds of 15,000 miles per hour, nearly halfway around the world. Titan II was developed under the management of the Air Force Ballistic Systems Division, forerunner of the present Space and Missile Systems Organization, and by the teamwork of several contractors. Space Technology Laboratories provided technical direction. Denver Division of the Martin Marietta Corporation developed and produced the airframe and integrated the 54 Titan II complexes. Aerojet General Corporation produced the hypergolic propulsion system using a fuel and oxidizer that ignite on contact. AC Electronics Division of General Motors Corporation provided the airborne inertial guidance system that can be programmed for pre-selected targets. General Electric Company's Missile and Space Vehicle Division developed the reentry vehicle. The launch facilities were designed by the Ralph M. Parsons Company. Titan II was conceived in 1960. The final squadron was delivered to the Strategic Air Command in December 1963. The missile and support facilities have been upgraded as the state-of-the-art has advanced. As part of a continuing crew training program, Titan IIs are occasionally launched from Vandenberg Air Force Base, California. Developed with the technology of 15 years ago by AFSC, Titan II is still one of our major deterrent forces. It waits quietly underground, its retaliatory potential available on a moment's notice. The YC-141B is a stretch version of the C-141 Lockheed STARLIFTER. It's 23 feet longer than the standard model. Aerial delivery testing of the YC-141B was conducted at AFSC's Air Force Flight Test Center, Edwards Air Force Base. The YC-141B uses the same dual-rail cargo deck as the basic aircraft, but it carries 3 additional 463L cargo pallets. Flight Test Center people experienced in numerous aerial delivery tests conducted this series. Standard C-141 checklists and procedures were evaluated as satisfactory for the stretch version. Among the tests conducted were extraction parachute tow tests. These included deployment, inflation, towing, and cutaway. This is a cluster of 2 28-foot diameter ring slot parachutes. Before live personnel drops, retrieval tests were made of 60 static lines with weighted bags. Tests on articulated dummies reduced the risk of injury. Personnel airdrop tests included 2 sticks of 8 jumpers dropped simultaneously. Army and Air Force jumpers with experience in the basic C-141 were used in these tests. Jumpers commented that there were only slight differences in jumping from the stretch 141 and the basic aircraft. Single platform loads weighing from 2,060 to 34,000 pounds were test dropped. Loads less than 15,000 pounds produced negligible pitch attitude change. More than 15,000 pounds produced definite aircraft pitch up, then pitch down. Aircraft pitch changes were about the same as for the basic C-141. On sequential platform tests, each load extracted the parachute of the next load. 3 loads with a total weight of nearly 70,000 pounds were dropped. It took 6 hours to rig the sequential drop in the aircraft, and only 11 seconds for the airdrop. The aerial delivery tests were successful. All objectives were met, and no problems in platform or personnel airdrops were encountered. The YC-141B, or Stretch Starlifter, brings increased cargo capacity and more effective use of Air Force resources. To further enhance the Military Airlift Command mission, the YC-141B, or Stretch version of the Lockheed Starlifter, was equipped with an aerial refueling capability. At AFSC's Flight Test Center, aerial refueling tests were flown by 8 pilots, including both Flight Test Center and operational pilots from Military Airlift Command. The Stretch 141B, with its 23-foot longer fuselage, was stable as it approached the boom. Boom operators from the Flight Test Center took the Stretch into position. Various boom disconnect positions were tested: center, right, and left. Various relative altitudes were evaluated, as well as combinations of gross weight, center of gravity, and airspeed. 275 knots proved to be the best airspeed for all gross weight combinations. Flight Test Center boom operators, experienced in numerous refueling tests, worked closely with the YC-141B pilots. Positions were verified by tanker director lights. Some 50 hookups and disconnects were made during the tests to verify the full range of acceptable speeds and positions for refueling. A chase aircraft was used for safety and photo documentation of the YC-141B and AFSC's specially instrumented KC-135 tanker. Among the final tests, a day-night evaluation was made. Receptacle illumination lights provided good visibility. YC-141B pilots reported excellent visibility from normal seat positions and no problem maintaining the boom contact position. Boom operators, constantly alert for receiver handling problems that could require boom separation, reported excellent visibility of the receiving aircraft and the refueling receptacle. The tests were successful, and a certified aerial refueling envelope was established. For the first time, factors contributing to damage and sustained fire from cannon hits in a potential enemy aircraft fuselage fuel tank have been studied under flight conditions. This study was sponsored by the Joint Technical Coordinating Group for Munitions Effectiveness. This group consisted of people from the Air Force, Army, Navy, and Marines. The study was conducted at AFSC's Arnold Engineering Center. Full-sized fuselage sections of a simulated enemy aircraft, complete with fuel tanks, were used in the tests. Simulated flight conditions ranged from 350 to 550 miles per hour, and at altitudes of 5,000 to 35,000 feet. True air temperatures were also provided. Interchangeable cannon barrels fired single rounds of 3 different types of ammunition, for a total of 23 firings. With loading complete, the area is cleared. Unusual pre-test planning and engineering reduced the high risk factor in this type of testing. 3 arrangements were studied: a full main fuselage tank, a full tank combined with an empty dorsal tank, and a fuselage tank with varying fuel loads. Closed-circuit TV monitored each firing, and motion picture cameras made a film record. These tests confirm that damage is influenced by airspeed, caliber of ammunition, and quantity of fuel and fuel vapors in the tanks. While apparently obvious, confirmation of these facts is essential to the design of cannon effective against potential enemy aircraft. This unique test facility is the first of its kind. The data gathered here will be useful in estimating both domestic and foreign aircraft survivability. A major Air Force objective is to increase the operational life of its systems. One means to this goal is development of new structures made of lightweight materials that are extremely reliable. AFSC's Air Force Materials Laboratory is using a technique called nondestructive evaluation to examine and evaluate these materials to ensure their high reliability. Some conventional evaluation methods result in destruction of the sample. The non-destructive evaluation group uses techniques and forms of energy to examine items without destroying them. An example is this high-power X-ray facility. Areas of interest are marked for positioning the X-ray source. Typical items for this activity are advanced composite wing and tail structures. In the ultrasonics lab, parts are examined using sound. Here, a turbine disc is examined for fatigue. A recording pen, operated by the scanning equipment, makes a drawing of the part, including its fatigue zones, cracks, and other defects. This is a 6,000 ampere magnetic particle test unit. It creates a magnetic field in steel parts. Very fine fluorescent particles applied to the part migrate to cracks where they can be seen under ultraviolet light. The latest techniques in electrical field eddy currents are used to detect heat damage in aircraft skin and cracks in fastener holes. Another way of finding cracks is the dye penetrant technique. The fluorescent dye is applied and soaks into the crack. Under ultraviolet light, the dye in the crack fluoresces. An X-ray image enhancement system clarifies features in normal X-ray films. The non-destructive evaluation group is an integrated mix of civilian and military specialists and technical consultants. In addition to testing, they prepare Department of Defense specifications for this type of work. These specifications directly affect the operations of hundreds of industrial contractors and government organizations. In addition, they can draw on the vast array of expertise in all disciplines represented at Wright-Patterson Air Force Base. This facility provides solutions to aerospace non-destructive evaluation problems. The benefits are reflected in the time and dollars saved by their methods in resolving questions of materials, quality, and integrity.